Okay, so we have studied last video until the types of intermolecular forces and the solubility, the factor affecting the solubility, etc. Okay, we have studied the hydrogen cells, right? How the sodium different hydrogen cells, how the hydrogen cells forms, and what are the types of intermolecular forces that are acting on the solution. We have studied in the last video. In this video, we will study further, which is the dual polarity and the effect of the solubility. We will study the soap property, why the soap can clean every types of the dirt, and then finally we will study the property of the solutions in gases. Okay, gas pressures, Henry's law, and etc. So let's go ahead. So dual polarity and the effect on the solubility, right? We already discussed it. The alcohol has dual polarity, right? See that OH, and this hydrophobic and hydrophilic both part. And the solubility increases. Look at that. This has the solubility decreases. Methanol can infinitely, you can dissolve as much as methanol in water. It has infinite solubility. Ethanol has also infinite solubility. As the carbon chain become larger and larger, solubility is getting the decreasing and decreasing, because the hydrophobic part actually dominating the hydrophilic part. That's why the longer is the chain, less is the solubility. Okay, so alcohol can be what? Many types of the alcohol. Okay, methanol, ethanol, propanol, butanol, pentanol, hexanol, okay, heptanol. So methanol means CH3OH. So CH3 is hydrophobic, H-phobic, hydrophobic. This is hydrophilic part. This OH can make the hydrogen bond, right? This CH3 part is, it has two parts. One is CH3OH, right? This is the molecular structure. So this part hates the water. This part loves the water. So this is the hydrophobic, phov, and this is hydrophilic. Hydro means water, fill. This is the philic part, this is phobic part. So that's why it has one CH3. Ethanol, CH3, CH2, OH. So this part is, okay, let me take the different color for philic and phobic. This part is hydrophobic and this part is philic. And the propanol, CH3, CH2, CH2, and OH. So blue is hydrophobic, red is hydrophilic part. Butanol, CH3, CH2, 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 OH. So OH. So this is hydrophilic. This must be large is hydrophilic part. See, this is hydrophobic, and the blue part is hydrophobic, red part is hydrophilic. Now pentanol, CH3, CH2, 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 and OH. So again the same thing, right? This blue part is hydrophobic and the red part is hydrophilic. So if you think about the hexanol, CH3, CH2, 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 OH. So OH. So red part, this OH part is hydrophilic and this whole part is hydrophobic. So hydrophobic part get increasing and increasing, right? See, hydrophobic part, in this case only the CH3, CH2, in this case only CH3, right? If you see that hydrophobic part, the heptanol. So heptanol, CH3, CH2, 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 CS2 CS2OH. So see, this is heptanol means 7 carbon. 7 carbon. Okay, so that much is hydrophobic, and only this much OH is hydrophilic. So see that this much is hydrophobic. So hydrophobic part increasing and increasing as the carbon chain increases. Okay, as the number of the carbon increases, hydrophobic part increases. That's why this is infinitely soluble, this is infinitely soluble, this is now solubility get decreases. Solubility of the butanol is larger than pentanol, pentanol is larger than hexanol, larger than heptanol. Eventually this is so big, right? It actually dominates the hydrophilic part. That's why larger alcohol cannot dissolve in water. So the question is, why larger alcohol can't, or very small dissolve in water, but methanol, ethanol, propanol, this short alcohol like methanol, carbon equals to 3, that is the propanol, carbon equals to 2, like the ethanol, carbon equals to 1, like the methanol, they can dissolve infinitely, means large solubility. Because in case of the short alcohol molecules, the hydrophilic attraction, means the hydrogen bond attraction, OH attraction, there is another OH, right? OH attract OH with the hydrogen bond. So the hydrogen bond attraction dominates the hydrophobic part, hydrophobic repulsion. So hydrophilic attraction dominates the hydrophobic repulsion. Okay. So but however, in the larger, as the molecules become larger and larger, hydrophobic part, or the repulsive with water, that is right, hydrophobic means that is repulsive with water. The repulsive hydrophobic repulsion between water and the alcohol dominates the total intermolecular force between the alcohol and the water. Okay, the intermolecular force is much larger. The repulsion between the water molecule, or the hydrophobic, this is the hydrophobic part, hydrophobic interaction dominates the hydrophilic interaction. That's why this cannot dissolve. But these can dissolve because the OH interaction, or the hydrophilic attraction with the water, is way larger than the hydrophobic repulsion. But in case of that, that's why this cannot dissolve. It has a very small solubility. That's the reason. Because of this part, hydrophobic. This is the hydrophobic part, and only this part has what? You can see that the dispersion force, that are weak forces, and the dispersion in the water is very weak, right? However, water has also dispersion, but every molecule has dispersion, but that's very weak. So the hydrophobic repulsion dominates that attractional forces. That's why it cannot dissolve this very large alcohols. Basically, you can understand like that. Okay. So we have done that. So let's predict the relative solubility. Okay. So sodium chloride in methanol, CH3OH, in methanol, or sodium chloride in 1-propanol, where the sodium chloride dissolve better, CH3OH or CH3CH2CH2OH. So ethylene glycol, for example, this guy in hexane, this is the hexane, or in water, this guy is better dissolved in water, or this guy is better dissolved in hexane. We have to decide that. Diethyl ether, this guy dissolve better in water, or this guy can dissolve better in the ethanol. Let's see that. Now let's see that. Okay, sodium chloride in now let's see that what is the what's first. Sodium chloride. Now let me erase these all. Okay, Now sodium chloride, where sodium chloride dissolve better in the methanol CH3OH, or it dissolve better in the, or it dissolve better in CH3CH2CH2OH, propanol, where sodium chloride dissolve more. Okay, where in which solvent sodium chloride has more solubility. Okay, so I think you may have guessed out, but if not, let's see the answer. Yes, of course, methanol, because the sodium chloride is the ionic liquid, ionic solute, right? Ionic solid. So it dissolves in polar solvent through ion dipole forces. Okay, but the methanol and the propanol have one polar OH group, but the hydrocarbon portion of each alcohol interact only weakly with the ions, and one propanol has a longer hydrocarbon portion than methanol. So I hope you have understood that. So sodium chloride cannot make the hydrogen bond, but it can make the ion dipole interaction, right? Sodium chloride is what? Sodium plus chlorine minus, right? So CH3OH, if you think that is what? CHHHOH, right? So that's why it has a dipole. This can create a dipole. For example, this is delta minus, this is delta plus. It has dipole. That's why this sodium can attract this guy, and chlorine can attract this guy. That's why sodium ion dipole. So ion dipole interaction, ion dipole attraction. So, but this dipole is stronger than CH3, CH2OH. It has also dipole, right? But this dipole is weaker. So the interaction of the sodium plus chlorine minus with this is weaker. But this is only the dispersion force. This portion is the hydrophobic force. So this has very weak, very weak effect. That's why if you elongate the chain, then sodium chloride also less soluble than the elongation. So that's why where the sodium chloride dissolve more. So methanol, ethanol, propanol, same as the water, right? Sodium water, in case of the water, hydrogen bond. In case of the sodium chloride, ion dipole moment. So methanol is CH3OH, and this is CH3CH2OH. This is CH3CH2CH2OH. That's why what will be solubility of sodium chloride? So this has the largest. This has smaller. This has very small. Right? Largest, the highest solubility among these three of the sodium chloride solubility is in the methanol, then ethanol, then propanol. Because as the carbon chain elongated, means the carbon chain become longer. So carbon chain become longer. This is CH3, CH2. Now see, carbon chain become longer, means that hydrophobic interactions are more dominating, or the dispersion force is more dominating than the ion dipole force. That's the reason, less solubility there. So now similarly, in case of the ethylene glycol in hexane or ethylene glycol in water, of course it has a hydrogen bond. See, OH is here, water has also OH. That's why hydrogen bond, but it cannot make the hydrogen bond with this. It don't have any oxygen. So that's why, yes. So this ethylene glycol will more dissolve in water because of the hydrogen bond. So now diethyl ether in water or ethanol. So yes, this water has, this oxygen don't have any hydrogen. That's why it cannot make any hydrogen bond. So it only can act through the dispersion force. So water has not dispersion force. Water has very tiny dispersion force. It has a hydrogen bond. It has a dipole interaction, right? So water has a dipole. So, but this don't have dipole, and this also has dipole, but this has this dispersion part. So because of the dispersion force dominating in this case, so the diethyl ether is more soluble in the alcohol than in the water. So I can ask you a question: oil in alcohol or oil in water? Where? So let me ask you one question. Oil, for example, propane. Let's say propane gas. Let's say hexane oil. Okay, CS3, CS2, CS2, CS2. This is oil. Okay, guys. 1, 2, 3, 4, 5, 6. This is hexane. This is the oil, gasoline. Okay, gasoline is different, but the octane, hexane, they are the fuel. Okay, liquid petroleum. Okay, this is the hexane. This dissolve more in water, or that dissolve more in alcohols. Alcohol is this CS3, CS2. So, for example, ethanol. Let's say CS3 oils. Where this dissolve more? Of course, this don't dissolve in this, right? It don't dissolve in this guy. It don't dissolve in water. So because this all portion has what? No hydrogen bond means dispersion force or van der Waals force or hydrophobic. These all hydrophobic part. And this has yes. This has yes. Why? Because this is the dispersion force. Because of this part, this whole oil can dissolve in alcohol but not in water. So now let's see some. These are the example. Cleaning ability of a soap. Why soap can clean? Let's see that picture of the soap here, the molecule of the soap. So soap is like this. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbon. 17 carbon. Let me write that in short form. Okay. Soap is like that. CS3. Oh, okay. This is not red. Okay. I am using the blue color for the hydrophobic. Okay. So CS3, 1, CS2, 2, 3, 4, sorry. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbon. And now let's see that. And look at this, COONA. This is okay. That's why it has ionic portion also. That's why C double bond O and Na counter ions also here. See, this is the soap. Or if you write that COONA plus COONA, right? Look at that. This portion is what? Hydrophobic. So it will love oil, and this is hydrophilic part. That's why this soap can handle both. If you have oily substance, hydrophobic, there are two types of substance in the nature. One is hydrophobic or hydrophilic, right? If you have a hydrophobic substance like oil, this will take care. This part will take care. If you have a hydrophilic type of the substance like sodium chloride, this part will take care. So it can wash anything. That's the reason. It can wash anything. Even it can wash the virus also. Because hydrophobic can handle the hydrophobic substance, and the hydrophilic portion can fill the hydrophilic. It has a both part, right? This is said to be the head, and this is said to be the surfactant. Now if you make the picture, the picture is like that. Okay, picture is like that. So picture is like that. It has a head, tail is hydrophobic, and head is philic. So head handles the hydrophilic substances, tail handles the hydrophobic. So that's why it can wash anything. So this is the wash or the property of the soap. That's why soap can wash anything. Okay guys. So it has both. Now if you see the solubility of some gases, okay, in given solubility of the gases in given water, helium has this, neon has this, nitrogen, carbon dioxide has this, oxygen has this, nitrogen has this, like that. And a boiling point also given. See, solubility increases, boiling point also increases. More is the boiling point, more is the solubility. Boiling point is directly related to the attractional force, right? Or the ion dipole forces. Helium cannot have any ion, right? And look at that, 4.2. Neon is also same thing, but it is bigger, that's why 27. But the nitrogen can have the lone pair, that's why it has 77. So carbon monoxide, oxygen has 90, nitrogen, okay, and the nitrous oxide is 121, like that. Okay, this is the boiling point increases, that is also increases. So now let's study the Henry's law. Okay, so what the Henry's law says, that the solubility of the gas, now we are studying the solubility of the gas. Okay, so what the Henry's law say, so Henry's law says that solubility of gas is directly proportional to the partial pressure of the gas. Solubility of the gas is directly proportional to partial pressure of the gas. So that's why S gas is equals to Henry's law constant times P gas. So last time I show you the soda water, right? So if the partial pressure of the gas increases, solubility of that gas also increases. Okay, so what is the formula for that? Solubility of gas in the liquid or water, for example, is equals to Henry's constant times the partial pressure of the gas. So how do you understand that is, let's see, CO2 in soda water, for example. So solubility of CO2 is directly proportional to the partial pressure of CO2. So that's why solubility of CO2 is equals to Henry's constant times partial pressure of CO2. This is the Henry's law. So let's see some application of the Henry's law, and you will like that, I think. Okay, see, scuba divers. Let's think about the scuba divers. Okay, right now we have the remedy of that problem, health problem, and scuba divers have some health problem. This is also the can. What happens is, once it has a more partial pressure, because when it was closed, this button was closed, then carbon dioxide is highly pressurized. The partial pressure of the carbon dioxide above that water is higher, is large. That's why it has a larger solubility. Once you open that, the partial pressure of carbon dioxide is here, same as like the atmospheric pressure. That's why before opening the button, you have a more solubility of the carbon dioxide. Means carbon dioxide is highly dissolved in water. Once you open that, carbon dioxide is less dissolved in water. Previously, for example, if solubility is 100 molecules in 1 ml, right now no 100 molecule of carbon dioxide in 1 ml, maybe 5 molecule in 1 ml. Okay, so solubility is directly proportional to the partial pressure of the gas. And let's see this scuba diver. What happens in scuba diver? So scuba divers go down, okay, on the ocean, and as they deep dive on the ocean, the pressure of the water increases, and the pressure of the water gives the more pressure on the wall of their body, right, and the skin of their body. Pressure of the water increases, and that water pressurized more, like this, okay, like this. See, I am pressurizing. So water in the all sides, right, from every side, water is giving more pressure to their body. So once the pressure increases, then the either carbon dioxide or whatever the gas inside our blood vessels have the gas, basically two type of gas, carbon dioxide and oxygen, right? Basically two type of the gas. and both type of the gas dissolve more in our blood. So scuba divers, if you test the blood of scuba divers, their blood has more carbon dioxide. Their blood has dissolved more carbon dioxide than when they come out. So that's why blood vessels, inside the blood vessels, more carbon dioxide get dissolved in their blood. So once they come out from the water, the pressure decreases, and according to the Henry's law, pressure is directly proportional to the partial pressure, right? Previously, highly the partial pressure of the gas is a lot. That's why that gas dissolved more. Once they come out from the water, partial pressure of the carbon dioxide decreases, or the pressure release. That's why carbon dioxide try to come out from the bloodstream, and blood can become fuzzy, and blood can have the blood clots, and a huge problem, health problem on those scuba divers. So that's why you can, for that you can have a good swimming suits, right? So that the pressure of the water less effect on that. And other thing is that you can add the inert gas like the nitrogen on your gas cylinder, so that not only the oxygen, you have the another gases also. Because of that another gases, that can balance, and you can get rid of that problem. So that's why very good blend of the gas, or the medically proven, and after research, the scuba diver right now nowadays they don't have that problem because of they have solution. And but in the back in the day, scuba divers have that problem. One scuba diver sometimes can be sick maybe in a 1 month, and back in the day, once they come out from the ocean. But right now it's not that problem. So this is the sample problem for Henry's law. So you can try this one. So partial pressure of carbon dioxide gas inside the bottle of cola is this atmosphere. What mass of the carbon dioxide dissolved in this? Okay. And the Henry's law constant is this. It's given here. Henry's law constant is given here. Just plug in the Henry law constant, and the mass of CO2 is this. Done. So that's way for this video, and we will do the next time. We'll do the next topic in the next video. Right now, thank you so much. Bye bye. Let's go to the next video. Okay. So in this way, we have completed this chapter 6 up to the Henry's law, and we have seen that how the Henry's law is applicable, right? The scuba diving one example, and the can soda dissolved carbon dioxide dissolved in water. That's the other example we have discussed here. And so one sample problem for the Henry's law, and this sample problem. Yeah, you should do these many problems in the homeworks also. And in this way, we finish the half of this week. And in the next chapter, next part of this chapter, the same chapter, we will go up to the we will study the concentration definition, like the ppm, pvm, molarity, etc. These things we will study. Then we will study the property of water as a universal solvent, and then electrolytes, mixture, colloids, and a preparation of the solution from the stock. And this is very important, and this is very useful. So that we will study on the next day and the next slides. Okay. So thank you so much for watching this video, and read that from your books also, and review these all of the topics in the PowerPoint given in the canvas, and search online, use AI tools. Okay, study about these terminologies. These terminologies on the AI, you get the lots of information. And you can use any book. So whatever the book we have recommended, you can study that. Also, you can study any book is fine. Open resources are okay. So thank you so much. If you have any question, please ping me, or don't hesitate to contact me. Thank you. Bye bye.